Are you at now?
No, I'm taking it in the spring. Yeah. No, I'm in operating systems, programming languages, and software engineering. It's fun. It's busy.
I wasn't.
She's like, Should I text her this morning? And honestly, the words, they don't really make sense.
Okay. So you're going to the convocation?
Yeah, I'm the
so-
flag bearer for.
Huh?
I'm the flag bearer for Pine Notes.
Oh, good. I'm planning on coming to see. So, yeah, the academic convocation is, there's some awards for faculty for service, for teaching, for scholarship. Presentation by last year's scholarship winner was Alan Lazard from physics. I think a student presentation, and somebody from the Board of Trustees gets up and says something. But, so, and kind of a feel-good, moment for celebrating some things on campus as the semester's going. We're in the 5th week, actually, of the semester, so it's moving along. So today we'll talk about a few regression topics, a little bit about correlation, an example, and a few other things. So I've posted a 5th homework that's up there. It uses 3 data sets, and it's based on some problems that are in the chapters 7 and 8. And so the problems kind of say, look at data and answer a question about, is there a significant relationship, is there anything else going on, and so on. So it's so I would suggest, for these 3 that the answers you write become kind of like a short report, like maybe a page, right? You might include 1 or 2 graphs, but then kind of discuss things, right? So that it's a little bit less, what's the coefficient, give me the output, but more kind of an explanation of what's going on. That's the type of skill that you need to develop more for use in a workplace or communicating to other people. These 2 are both on some bees and pollens, and there's a couple others that are there. These self-study problems I thought were decent. You can look at any ones there. They have little short answers in the back, but I kind of found those were interesting ones. Not that the others aren't good, but in any case. So you could, these 2 problems, because they're on the same topic, could be combined in kind of one report. So it's kind of like looking at these 3 data sets and doing short reports. They don't have to be extremely long. You don't have to necessarily go into every possibility, but just kind of use the statement of the problems as guidance or something that you might look at and go with that. Online, the 3 data sets are here, or if you have that library command, they can get into R, or I kind of put them in this .r data. Open that in R, it'll have all 3 data sets in there. And the script here doesn't give you everything that you might want to do, not all the commands, but at least it gets you started with things. So in this, it loads the data one way or another. If you attach the data set, I guess I could put that later, then it's easy to refer to the variables. And there's fitting a few plots here. So you might investigate 1 or 2 other things with that, but it doesn't have to go extremely extensive beyond that for answering the questions and presenting these simpler data sets. And for the student topic, the student up for the next one is Yifei. Yang on this. And so, but everybody can look at this if they want. The topic is based on one problem from the book. There's an X and Y variable there, and the book suggests to transform the data. Well, I wonder if it's useful to do the transformation. So it's kind of looking at another problem. What's the impact of transformation in the regression context? And so there's a few questions that are there, but they will have that prepared for next Wednesday. So tying in with the theme of looking at transformations and data and how it impacts different things that we're doing. So the other thing that's coming up is the project, and I've not written up a handout about the project, but we can say a couple things about it. It's due in, I think, about 3 weeks or so there's some time. The idea is to take a data set and apply one of our methods that we've done a little more extensively, or maybe compare, contrast a couple methods on it, graphical presentation, some statement of a purpose of looking at it. We've looked at things with one sample, things with 2 samples. We looked at one-way ANOVA. We're looking now at simple regression with one predictor. By the time the project is done, next week we will look at some things with multiple regression. And some of you have a little more background in multiple regression. So you could do things there with multiple predictors as you want. It would be desirable in this to compare methods to some degree. Right? So for instance, in the 1 and 2 samples, we had the T procedures, 1 sample or 2 sample based on T distributions. We also had some Wilcoxon, some rank, some test here, or we had assigned rank procedure for matched pairs, like this. There's Kruskal-Wallis was for ANOVA. For simple regression, we haven't really talked about alternatives to the linear model, but transformations do a little bit like that. There are some kind of smooth functions that maybe we'll talk about, or if you have used regression in another class, you could do. So there's a few different ways to go. And I'll think about data sets to kind of suggest one. I'm kind of interested in, the book has the data from the 2000 presidential election where George W. Bush, H.W. Bush was elected over Al Gore, and there was this big dispute. So this was a huge thing back in 2000 because basically the Supreme Court declared that George W. Bush was president while they were still trying to figure out problems with the ballots. There was this kind of butterfly ballot thing that kind of opened like this, and part of the thing was down here and part of it was up here, and it was kind of funny across there, and so some Florida counties had very funny results in terms of things, and they had these punches that were going through, and there was supposed to be a machine reader, but if you didn't punch all the way through, it might not read your ballot. So there's a lot of problems with the technology and things, and then there was a lot of efforts by the Republicans in Florida to exclude certain people from the polls, disqualify them. So there was kind of all this mix of things going on. There's a couple data sets that are in the book, but the report looking at 180,000 different ballots was done by NRRC at the University of Chicago National Opinion Research Center. So those data some of those data are available online. I haven't used them, so I don't know how easy it would be to use, and if it would work all that well for regression. But if it's I'm kind of intrigued, so I think I'll try to grab that over the weekend. They might have some graphs and nice reports and things like that. So a project, in addition to looking to a data set, might critique the statistical analysis that's involved in something like that. Anyway, so my plan is then on Monday to talk about that more, and there's still a couple weeks to do something. This would be writing something up, 5 pages, something like that. It doesn't have to be massively long. Maybe it's 4 pages of text with a few pages of graphs and computer appendices. That's a report that states something you're interested in about a data set, describes the data set, and fits one, probably a couple different models, examine things in a couple ways, and then states a conclusion. So it uses the tools we've done to come up with a conclusion and then justify it, paying attention to some model assumptions and things that might be there. So. But we'll talk more about that on Monday, but I wanted to say a little bit more about it. If you're thinking about data sets or things that you're doing, that's fine. Now I know some of you are working on senior projects or other things. There's a data set you're using for one of those projects. It could be used for this one as well. This can be done, you wouldn't be necessarily comparing methods or writing about them quite the same way as you would be for that. But if you started working with a data set or something related to that, it could be made into a project that would complement things going on there. So, but any questions about the projects? We'll give more. We'll check the timeline and also give more something written up as details for Monday. Okay, a few topics in regression. The first one, regression does not mean causation. Right? Just because you have a relationship between two variables that even looks quite amazingly strong, right? It doesn't mean that changing an x value will necessarily change the y value in a way that you would predict, right? Sometimes x and y have a common cause. Size often can be that common cause. Bigger hospitals have more patients, more sick patients, more healthy patients, more expenses, more nurses, more of everything, right? And so all the size variables are correlated, but it doesn't mean that if you put more nurses in there, or you pay for more doctors, or you pay for more beds, it's necessarily going to have a positive outcome on other things, right? So there can be things that are common or have something underlying, and at the same time putting resources into paying for, you do a regression of test scores on amounts spent on education. Just because you pump more money in, even if the regression says that there is this positive relationship, doesn't mean that it's fundamentally going to change things. Maybe there's something underlying about the communities that are spending more, have more of a culture of paying for education and doing more for education. So it's not just the money, it could be everything that goes along with the attitudes of the community, and just the state allocating more money to certain areas might not have as big of gain as you would hope. It could, maybe there is a deficit in funding, and so the partial of the effect would be, you'd get part of the effect, but you have to be careful not to say that you really think that it's going to cause that. Maybe a randomized experiment where you really can control things, control levels, like in an engineering setting. Maybe that's more where you would think that it would actually cause something. Now there is causal relationships. X does cause some Y's, but it's hard to infer that from an observational study. A second topic is correlation in a number of fields. Between X and Y, things are summarized in correlation. So the sample correlation is usually given by R, and the formula for the sample correlation is xi minus x bar, yi minus y bar, over the sum of xi minus x bar squared and that's times the sum of yi minus y bar squared, and the square root of all that. That's one way to write the sample correlation. If you divide by n minus 1 in the numerator and n minus 1 in the denominator, and kind of put one in front of each of those, in there is the sample covariance of the x and y's. And then this thing is the standard deviation of the x values and the standard deviation of the y values. So it can be written like that. It's a covariance divided by the two standard deviations. Right? Covariance in the numerator, right? It has all the units of x and y. So if x is in miles and y is in thousands of dollars, then the numerators in those two units multiplied together. And that doesn't, you change from kilometers to miles or dollars to thousands of dollars, and or to Canadian dollars, right? And then the units up there change. Standard dividing by the standard deviations removes that. And so this correlation, R, is a pure number in that sense, a number without units. And it's between -1 and 1, and the interpretation that's given to it is, R will have a value of 0 if there's no linear relationship. In the data set. So it's not going up, it's not going down. It might not be completely flat, it might be wiggling, or it might just be a big mess with no pattern to it. Or it might be a cluster here, but arranged in a certain way so there's no distinct pattern up or down. 1 is perfect relationship, so when it's 1, all the points have to be exactly on the line. And if it's like that, so it's sloping down, right, between x and y, perfectly on the line, R is going to be -1. And sometimes it's hard to exactly eyeball from a scatter plot how strong it's going to be, but looking at enough examples, you kind of get an idea of what the correlation of 0.8. It's a pretty distinctive relationship up there. Correlation of 0.3, it can be almost a little hard to kind of visualize it. You have to stare at it a little while and imagine it sloping up a little bit. So there's kind of near 0, plus or minus, is a little hard to tell. Yeah?
I might have missed this, but what's the difference between the two? The -1 and the 1? And, where are the dots?
I should have just drawn it the other way. So,
Okay.
Yeah. I think I was kind of drawing from the side here. I was kind of, it's supposed to be right on the line.
Yeah.
Yeah, and it's supposed to be sloping down, right? But that was kind of my visual going back and forth, and I got confused. So. Right. One other way of writing this thing, the standard deviations. If you divide by n minus 1 and n minus 1 here, you get the sample variances. Right? You can pull, that's just a number. It doesn't depend, once you sum over all the i's, you can pull that inside, so you can write this thing as, it's not that big. Get it, get xi minus x bar. Trying to write small with this. Try it again. Summation over here. Xi minus x bar over the standard deviation of x times the yi minus its average over the standard deviation of y. So all of that is inside the summation, right? And it's all divided by n minus 1. So correlation, you can have kind of the standardized difference of the x's times the standardized difference of the y's, and kind of that relative magnitude, and whether they have positive signs together, then you're adding up positive terms, or if they're both negative signs in the numerator, then you're adding up, again, something that's positive, and you get a positive correlation. Correlation is related to regression, right? So if you have a positive relationship, you're going to get a positive slope. If it's negative, you're going to get a negative slope. And the equation for our b1 hat this was the sum of xi minus x bar, yi minus y bar, over the sum of the xi minus x bar squared. We're predicting the y direction, so it's not symmetric in x and y. This is equivalent to the correlation times the ratio of the standard deviations. If you work out the one, right? So this has an important interpretation, and this is where the idea of the term regression came from, right? So that if you have if x changes by 1 unit, right? Y does not change by sy over sx, but instead by less than that, y times is r times sy over sx. So assuming r is positive, right? So if you imagine that if you go up a certain amount on the x, how much do you go up by y? Well, you don't go up kind of the ratio of the standard deviations, kind of a 1-to-1 change there, but it's less because of correlation, right? The correlation is typically between 1 and -1. So the interpretation of that, called the regression effect, is important to keep in mind when looking at results. Right? So if you imagine that there's an example I've used in some other classes that I might have used with some of you, that if you have a bunch of intersections and they have a number of accidents, 1 year, and you go in, you take the ones that are the worst in terms of the accidents, right, and go in and put in traffic abatement things. You put in new signs, new warnings, brighter lines. Maybe you make the lines a little bit narrower. That's called calming. It's kind of, people slow down when it gets more narrow. And then the next year you see fewer accidents. Is it because what you did caused there to be fewer accidents? It might have had some effect, but part of the effect will be this regression effect, right? That the ones that are so far out 1 year, where are they so far out the next year? Well, not necessarily. They kind of regress to the mean. They kind of slip back because of this correlation. Right? If you're choosing things that are at the extremes, they're still, and there's a positive correlation. They still tend to be kind of high on average, right, above the average again, but they're kind of pushed back. Part of this is the geometry of the problem, is that it's not symmetric what we're doing. We want to minimize the errors in the y direction. So I'm kind of doing this little twist thing, because if you have a scatter plot of data, right, a line that has the slope, that is the standard deviation of y over the standard deviation of x, would kind of go through this longest direction in here. Right? That's eventually in chapter 17, chapter 17, not 117. 17, we'll talk about principal components. And that it finds a dimension that's the maximum variance dimension from combining the two variables together. Right? And so that would do this longest distance here. The slope that is used in regression, because it's not symmetric in terms of x and y, is this correlation times this ratio. And that one is a little bit more like this. Right? It's supposed to, right, kind of a little bit depressed because of the correlation. Right? So the ones that are very, very high in terms of the x's, they're still high, but not quite as high as if they've been kind of an equal trade-off. And that's just the algebra of the regression equation, and it's something that just happens in all circumstances. You have a retest situation. You take the highest or lowest. They tend to be extreme again, but kind of pulled toward the center. Right? Other ones that were, that weren't quite as low. The next time you measure them, some of them pop up and are the biggest. So part of the effect is always that. So how do you get around that? Well, you never get around it, but you might do more of a comparative experiment. Right? If you had some places where you did the intervention, some places where you didn't, you would see a regression effect in both places, but you might see an additional effect in the places where you had an intervention. So having a comparison group is really important to measuring that regression effect. So let's say that. So comparison groups are important for assessing regression effect. And since it's not causation in many cases, you have to kind of think about there might be other things causing that and just max, right? So many fields will test for correlation in addition to testing for the variances, right? And we can do that. Right? So a population correlation then would be the parameter. These are given by rho, Greek letter rho. It might be written as the expected value of x minus its mean times y minus its, so that's the covariance, its mean divided by the standard deviation of x and standard deviation of y. It's kind of a similar formula, kind of the theoretical correlation. What is the real association in the population? And then with data we have the xi, yi pairs going from 1 up to n, and then we calculate our sample statistic R. And we want to say something. Where do we think the population correlation really is? We can do confidence interval for this, we do tests. Right? And but some of the critical things about testing is what do the data actually look like? Are our data, our x and y bivariate normal? Bivariate normally distributed. If they are, then the scatter plot between x and y kind of looks like a rugby ball or a football or basketball or something like that. It's kind of this point cloud, right, where there's a center. And then if you mapped x down, it would look like a normal distribution. Right, it kind of looked normal over here. And if you mapped y over that way, it would kind of look like that. And actually, if you map it to any plane cutting through the space and projected it, it would look normal. Right? But it kind of looks like this point cloud. In multivariate statistics, you kind of sometimes do level curves. Right? There's kind of a center here, and it's kind of like a bell-shaped curve, but it's kind of like a mound, right, in 3D. And it's falling away in terms of the likelihood of seeing observations. Kind of at the center with decreasing chance of being away from the min. And the correlation gives you the tilt in this, right? If they're independent, it's just a round ball and there's no tilt. But if they're correlated, then it's tilted like that. If it's something like that and not too different, if yes, right, to test the hypothesis that the correlation is 0 versus that the correlation is not 0, you can calculate a t-statistic. The t-statistic is the correlation, but you have to standardize it a little bit, and this is the transformation that gets done. Then this thing under the H0, this t-statistic is distributed like a t-distribution within -2 degrees of freedom. So if this t-statistic ends up being very large, right, bigger than 2 or less than -2, we would reject the idea that the correlation is 0. When is this big? Well, the correlation has to be away from 0. The further it is away from 0, if it's close to 1, this is almost 0 in the bottom, right? So you get 0.9 here, 0.9 squared is 0.81. 1 minus that is 0.19. So you're almost, you're multiplying by a bigger, you're dividing by something that's smaller the closer you are to 1 or -1. And the sample size. So the statement of conclusion would be reject H0 if H0 if our t statistic, or the absolute value of it, is greater than the 975 percentile of an n-2 degrees of freedom. So you can test for 0. If things don't really look normally distributed at all, right, and X or Y is skewed, or there's outliers or other patterns, this test might not be so accurate. So this test, this sample R, is called the Pearson product moment correlation. So Carl Pearson in the early 1900s wrote about this, wrote about the test, wrote about the distribution, right, and used it. So based on the XY data directly is the Pearson correlation. But what if you can do if it's not normally distributed? If it's not normally distributed and there's outliers, then X bar or Y bar might be extremely affected, standard deviations might be extremely affected, and so it's very sensitive. Right? So the alternative is ranks. Spearman's correlation. Right. The xi's are computed to a ranks for the x's. The yi's are, you rank the, so instead of having the xi, yi data, you have data that are ranks, pairs of ranks. And then we compute correlation, the same sample correlation formula using ranks. And do the same t-test that you had before. The impact of using ranks is that, if it was skewed or there was a few big outliers, they're not sticking out. The ranks, these are going to be numbers 1 through n, these are going to be numbers 1 through n, and there's not that outliers out there. So, social sciences, psychology, I think that because Spearman and some of the other people were psychologists, very popular to use in those fields. And in R, there's a command correlation.test. And you could tell it either to use Spearman, or there's another one called Kindle, or Pearson. You can tell it to do the different correlation methods, and it will do the ranks for you. Right? But these tests work out if the null hypothesis is true, right? There's other things that you would do if you want a confidence interval that we can talk about. But anyway, I think I want to kind of move on to at least looking at one data example, given the time. But anyway, correlations could be a focus in and of themselves for some fields and endeavors. But I thought we'd look at doing some of the regression in R. Right? So I thought I would get a new data set. So I think about different things, like counties. Well, I could do Vermont, but no, actually let's do Nebraska. I'm originally from Nebraska. I was born in Lincoln. Lived there for 18 years. And so here is a maps of Nebraska, right in the middle of the country. Right? And these are the counties. It has 93 counties, mostly square, some of different sizes and things like that. And so we might want to relate county area size to population. Right? Do bigger counties have more people? Yes?
It's more of just a random question, but is there a reason why the county 66 is so much bigger than every other county?
Yeah, this is a Cherry County up there.
Like a significance, test the difference between those. I bet it'd be pretty significant.
Yeah, so that's just up in the plains. These are the Great Plains.
Okay.
It's just, well, we'll see, but it's just open land. It's kind of,
I mean, I figured, but like, that is a lot bigger. Than
that's a lot bigger, yeah, it's enormous, right, and so Vermont would fit into like part of the segmentation, but, so just off different websites, you can grab the data, and I plopped it in here. They have the county seat, the census of 2010 in some of these counties. Nebraska counties also, their license plates also start with a number, that is the county number. So driving around Lincoln, there's all these twos, because Lancaster County is county number 2 in that counting. And so they all have a license plate. It's the Platte River goes through Nebraska, so I don't know if this was supposed to be Plate or Platte or what, but it's kind of funny that that's kind of Platte mistyped, because the Platte River goes clear across Nebraska. And then some of them have county fairs, right? So that was there. And then I grabbed from another site, had the counties and then the land area. And so when I initially grabbed these, they had a little comma in there, like 1,075.29, so I had to change the numbers to match that. But anyway, the counties map together there. Right. So you can read that into R, and I did. Right. And the first few rows, here's the county seat, then the census 2010, the license plate number is a link to where they have a county fair. Effectively, you could make that into an indicator. Is there a separate county fair in that county or not? And maybe that the county name again, and then area that's there. So here are, I think I attach that so that we can use just the names. Make that big, pull this over a little bit. This is what the 2010 census looks like by county. That's where Omaha is, that's where Lincoln is, Grand Island, Hastings, so the different cities. So we might want to take logs. Logs, it looks like this, of the population. The census, there's 1,825,026 people, a little less than 2 million in the state. All right? In terms of area, this is area by county, here are the areas. There's Cherry County, County 66, right, this is up there. Again, the logs make it look much more reasonable. There's 76,000, almost 77,000 square miles. Nebraska's about 400 miles across and 200 miles wide. There's a sign driving in from Kansas that says Omaha, 444 miles, so when you cross the border. So it's pretty long. If you plot area versus census, right, the plot is dominated by these outliers, right? This is the outlying area, these are the outlying populations, and so it doesn't look like the regression assumptions at all. This one would particularly be called an influential point. We'll talk about diagnostics, and this one is influential because you want to draw a line through these points, you have to pay attention to the vertical direction. So if you draw a line that's going out here, it's going to miss totally, right? And so it's going to have to basically, this one's going to pull the line down towards that. You can't draw it totally flat here because it misses that one so bad, right? We get penalized by squared errors. So this one's going to be influential and pull it up. This one's going to be really influential and pull the line right over to it. So it doesn't look like it's going to work so well. But let's do log of both cases, and we get something that looks like that, right? So the log of census versus that looks, much more reasonable for regression. If we try to predict the population on the log scale, right, we get this regression, and it's not, so here's the intercept and slope. So on the log scale, it's 10.78 minus 3.155 times the log of area. Its standard error for this coefficient is here. Standard error for the intercept is here. If you take the ratio of those, you get t-values. There are 93 counties, so there's 91 degrees of freedom. A t-distribution with 91 degrees of freedom. The 0.975 cutoff point is 1.98. 1.98, right, 6. Right? So if we get the t-values in testing that are bigger than 1.98, we'll reject a value of 0. So for the slope, we get negative 1.149. The p-value, this little symbol here means the p-value of 0.25 is not small. Right? So if the coefficient on the log of area was 0 and it made no difference at all in the predictions, we could get something as extreme or more extreme than negative 0.3155 just by chance, about 25% of the time. That's not surprising. So there doesn't seem to be much of a relationship. The intercept, though, you know, none of our data values are near 0, right? And so, you know, mapping this over here, well, there's no way we're going to get a 0. Well, it's kind of a far map to go all the way back to 0. Sometimes you get a significant or non-significant or even negative, intercept in a problem that couldn't physically have a negative intercept because you're doing such a far extrapolation. And that doesn't really mean that it's bad. The data has to fit in here, right, in this area. So if you map it back and it happened to go below 0, and that'd be nonsense, you know, you wouldn't really worry about it. Mostly you'd be interested in change and the slope. So that one's not there. Some things you can do in R, you can do confidence intervals, and I'll do a confidence interval for the log area or that. You can put the line, the regression line, on there, so it's sloping down a little bit. You can also get the residuals, the errors. The errors or the fitted values. Here I'm going to do points. I'm going to add points to this line, to this picture. The x value is still this log area as before. The y value is going to be the fitted. Where are those fitted values going to be if I add them to this line? They should all be on the regression line, right? So the fitted value or predicted value for this one's going to be right below here. We should have 4 kind of clustered here and then a couple like that. If we do that plot, right, those are where the predictions are. How big is the standard deviation this way? And our model had our errors, had that sigma. Right? It's part of something that's produced by the sum rate, and it's just called sigma. So that value is 1.34. So on a log scale, the standard deviation of these vertical distances is 1.34. Right? So if you think about, you know, here's 9, 10, 11, you know, so kind of about 2.6 or so. If you imagine kind of a bar of about 2.6, you know, that's most of the points and most of the points along here, right? Maybe there's one that's a little bit bigger, maybe 1 or 2 that's certainly bigger. But out of the 93, having 1 or 2 bigger is not so, you know, unusual. So they just generally kind of fall within that plus or minus 2 sigma band. I think that's given here. So the residual standard error is what it's called here in R. Is the 1.34. We'll study R squared. You know, the percent of variability in the y is related to this. Only about 1%. That's not very good. The correlation's quite small. Let's do correlation. Correlation of log census 2010 versus log area. This is negative 0.12, pretty small. So core dot test. Right, if you tested that, gives a t-value negative 1.1415. That's actually the same t-value we had up here. They'll give you the same value. There's only one predictor of correlation. It's all about linearity. Slope of 0, correlation of 0. Same p-value. Confidence interval for correlation out of that includes 0, so it might not be related. Let's think about doing predictions and confidence intervals for predictions. Right? I said, well, what if we had a county that had was 1,000 square miles, right? A little over 30 by 30 square miles. Right? So the log of 1,000 is 6.91. So 6.91 is going to be here, so our prediction is going to be up here in the middle. Let's contrast that perhaps to, how would we get that from the regression equation? In the regression equation, we had these numbers, so it's 10.78, 10.78 plus or minus because it's negative. And then the slope in there was 0.3155, so 0.3155 times, now you put it on the log scale. So there's 8.6, so if we want to put a points on there, log of 1,000 and our 8.6, and let's make it red. And we can change the plotting symbol to X, right? Right, there's our prediction for that point. Now, if we actually had a county that had a census, we could calculate the difference and get the error for that particular point, but I don't have a particular county in mind. At X equals 10,000 though, what if we had a county that was 10,000 square miles? Or maybe this is a group of counties. Right? Perhaps you'd have some of these counties grouped together. The population's so sparse out there that some counties don't have schools. I mean, like a high school, like in Vermont, you might share across districts or something. And so they have a hard time doing some basic services because you put a few hundred people out in 10,000 square miles, and it's pretty hard to pay for long distance service. So maybe they group together. What if they group together? Well, 10,000 square miles is a log that's a little bit out here. The prediction, if it was 10,000, it's the same regression equation, but now this new one, 7.87. So in the vertical, that one, I can kind of show you, can't see exactly where it would be if you don't go out that far. That'd be, if we put a horizontal line at that 7.874, I'll make it dotted, right? The prediction would be somewhere out here, right? A little bit outside of there. So we can do the predictions, but we might want to do a prediction interval for that, right? So you can take out the different pieces that we can do with some work, but there is this prediction command. So if you just put, to do this, it's convenient just to save the model output. Save the LM command as mod, or for short for model. And then if you predict mod, you can get standard errors. Now if you just do it like this, it's going to do a prediction for every single county. So if I do this, right, for all 93 counties, it has the fitted value on the line, right, the predicted value for my 93, and the standard error for those fits. And we could do something, right? So the fits had to do with how far you were away from the center, right? So that the fits, the standard error should be going up as you go away from there. We could work to get a plot there. We're all, maybe we can, that will go on. Right? But if you tell it, give it this object from fitting your XY data, and then tell it it has new data, where am I getting this stuff? In the prediction command, there's a little bit of help file. Oh, predict, not that predict, there's a predict.lm, right, for a linear model. There's a version of predict that where there's new data, standard error, a fit. Do you want an interval, confidence, or prediction? Right. So if I give it new data, it has to be in this form of a data frame. It wants a data frame. And it wants variables identified as the ones that are used in prediction. So you need an X, you need area. It's kind of neat, I can give it area instead of log area. It will convert it for me. Smart that way. And if I tell it for standard error equals true, it'll give me the standard errors. Confidence will give me the confidence level. And so for these 2 points, it has my fits, and it gives us lower and upper intervals for prediction of estimation of the mean at that level, and standard error for those. Right? But that would be if I had, that would be appropriate if I was taking several different units at 1,000 square miles or 10,000 square miles. That'd be the average prediction, right? But if I only have one county, right, then I want prediction for a single. So it's not necessarily on the regression line. The average is on the regression line. So I need to have more. So it knows that we want to do prediction intervals if you tell it prediction. So if you run that, it gives you intervals again and standard errors. But now the standard errors are those bigger than they were. No, those are the same as before. But what it's done is add the residual standard error into it, right? It's added that extra bit. So now 5.9 up to 11.2, previously it was 8.2 up to 8.9, right? The regression line pretty accurately predicted, but an individual observation has that plus or minus 2 sigma that you'd have to take into account. So you can do a lot of those things with the regressions, and so in this next homework, some of these commands you can use to do some of the graphs and so on. But the area doesn't really relate so well to population, because some big counties with area that have large populations and have smaller populations and so on. There's this other variable, license plate, right? So it's just 1 to 93. If you do a histogram, it looks like that. If you sort that thing, 93, in maps in Nebraska, the Platte River goes from here right across. It's kind of, like I said, kind of funny that they called it, it's Platte there. I don't know if they're called license plats or plates or whatever. So, but since it's there, why don't we regress that census on that license plate number? Right, so here's the regression of that. What? Look at this. It's a significant relationship. That license plate seems to predict the population size. Why would that? And that was just the pure census. What if we take the logs, we get something. So that's significant as well. Why in the world is that going on? So if we change the license plate numbers, will it change the population? No. Right. So these are the license plate numbers, and this is population. Right. That's the census, right? So what's happening? Why are we getting a significant relationship here?
Probably because the license plate numbers were determined by the population of each county.
That would be true, right? So if you did choose the largest ones and then do that, right? These are the license plate numbers, a picture of them here. And so one's over here. Omaha, Nebraska is right there. Right? And then Lincoln's right here. So at one point, Omaha was kind of before it became a state, was the dominant place. Right? It had the Missouri River runs down this side. Right? So it was big for trading. Railroads were going through there and then the Platte River was coming this way. So that was the big trading place. So that was the biggest population. Right? So that's over 500,000, right? And then Lincoln is here in Lancaster, number 2, and that's 300 million now or something. But right, and then this is south of here, and that's also pretty big. So and then 4, is pretty big. Oops, that's going to go to the. Right. So you have a few of these that just happen to have. They were the politically dominant ones, so they took numbers 1 and 2, or 3 or 4 close by. That must not be a 4. That's 41. 4's over here. And then some of these that are out here in the farm country, particularly the ones that are up here in the west, that's the Badlands, south of South Dakota. It's sandy soil. You can't grow crops there. There's a weather gradient that goes across. So you can have, in Iowa, you can grow crops without irrigation for a while. But then you start to have to irrigate, and then there's these big pivot irrigation things, and then it becomes too sandy, and they just let animals wander. So if you look at maps, because that gathers your maps out here of these counties, it doesn't list roads. It lists farmsteads, houses. So it's like, here's the road that goes over to Butler's place. That's all there is, right? And so that's why you get a couple hundred people in these massive counties. So it just happens, right, that 1 and 2, and then this one's pretty small too, right, are the smallest ones, small numbers, and it's just, that's the way it is, right? So if you do an AB line of this, what does it want, where does it want to put the regression line? It wants to, oh, it's pretty flat. That's the, oops, that's a, let me do that again. This is the, let's just try this plot. I'll try to do a plot again. So that's the census. So if I do a regression on this, of just the census number, not the log on there, that's where the regression line goes. So it's just pulled up. It's pulled up enough by these dominant points out here to be called significant. It looks almost flat, but 93 points, it seems to be that way. So anyway, or the summary of this case was also pretty dominant. So it's doing a good job of predicting these ones out here. So it actually gets an R squared of 0.72, 72% of the variation, because it's pretty accurate for all of those. If we do a plot of license plates with the log scale, it looks incredibly good, right? But these are all quite small out here, and particularly some of the 90s, up here 80s that are really far out in the farm country are very, very small. And it's just, that's happened, started here where the population is, a number going out, and it ended up giving us a different relationship. So you can get kind of interesting things for different relationships there. But anyway, there's the picture again.
I find it interesting that 4 is surrounded by a lot of the lower numbers.
Yeah.
Especially the top left.
Right.
I don't know.
So some of it would depend, as 4 is pretty big there. So Custer County, Broken Bow, I don't know. North Platte is a fairly large city. I mean, as far as things go. And Ogallala. So the Platte River comes right, right through the middle of here. There's a big lake out here that's going by. Overuse of water, but anyway, that's the kind of the story for today. So, and so Monday we'll take up more things with diagnostics and talk a little bit more in depth of exactly what to do with the project and so on.
I totally forgot to give this to Hattie as part of my homework.
Oh, okay.
For Wednesday.
All right,
But
sure.
I had it done. I'm sorry about that.
Oh,
This
that's
is
fine.
probably
Thank you.
I don't know, what would we define as the defining character?
Will we consider Hyannis simplicity?
I feel like if you have like public buses, then you can be qualified as safe.
Or taxi?
That's
Yeah, I feel like public transportation other
Yeah.
than just like schools.
yeah. Then of course that's sick.
Parking garages too. Industry.
Yes. You.
So, for the presentation, I just need to follow.
Yeah, so that would be kind of the idea. Kind of look at the data, look at the impact of logs. Does it seem to change things terribly much? Are the regressions, does the significance change very much? If you predicted for a particular value there, right? If you predict on the, if you're doing on a log scale, you would take the log of that value, predict, and then take the anti-log, right? Reverse it. And so that would be kind of interesting to see how it goes.
What's the code?
Just e to the power, right?
Oh,
Yeah. So this one, it doesn't look like there's much, I don't know why they're taking logs in this case. I mean, it doesn't look too bad in this case, and so I don't think things will change all that much. That's okay, sometimes there's a result where it doesn't change as much. They might have some rationale for taking logs, and I just don't know what it is. Maybe to read through the problem, there's maybe some explanation I just didn't quite get. But, sometimes people take logs, or there's a problem there, and, so maybe you'll find, see if there's much of an impact. There might not be, but that's okay. Yeah, so.